So as we've talked about previously, our conservation of energy or energy balance equation is the fundamental way that we keep track of energy for a mechanical system. Well, I can rearrange the terms here. And so if I take these two initial energy terms over to the other side of the equation, then what I'm going to have is the work done by non-conservative forces is equal to final minus initial kinetic energy plus final minus initial potential energy. This first term is obviously delta K, the second one is delta U, and delta K plus delta U is nothing more than the change in the total mechanical energy of my system. So I can rearrange this equation to think about how the total mechanical energy of my system is changing, and what this now says is that the total mechanical energy of your system changes based on work done by non-conservative forces. So keeping track of how the energy changes in a mechanical system is all about keeping track of the work done on the system by non-conservative forces. Conservative forces can change how the energy is stored within your equation, but it's non-conservative forces that change what the total energy of your system is. If the work done by non-conservative forces is zero, then that means the total energy of your system doesn't change, and therefore we have conservation of energy. Well, we have a very similar equation for thermodynamics. This is the first law of thermodynamics, and what it tells us is that the change in the internal energy or thermal energy of our system is equal to the transfer of energy into or out of your system as heat minus the work done by your system. And so the first law of thermodynamics says there are two ways that you can change the thermodynamic energy of your system. You can either transfer energy as heat, or there can be work done. And so we'll emphasize in a minute that talking about the work done by your system versus on your system, how that matters. But for starters, let's think about Q. And so Q is the energy transferred into or out of your system as heat, and we're going to use the same convention that we have so far, which is that if energy is transferred into your system, then Q is positive. When energy is transferred out of the system, Q is negative. So energy transfer as heat is one way that we can change the thermal energy of a system. The other way is through work. And so here we want to be clear whether we're talking about the work done by the system or the work done on the system. Those two things are related. One of them happens to be negative the other. So the work done by the system is equal to negative work done on the system, and we'll see in a second why that's the case. When you look up the first law of thermodynamics, you might see an equation that says delta E equals Q plus work. So there may be a work term over here, but this is a plus sign rather than a minus. If this is a plus sign, that means that that equation is framed in terms of the work done on the system. We're choosing to frame it in terms of the work done by the system. So let's think about what's going on here. So here's a cylinder. My system sits inside the cylinder. It pushes up against a piston head, and that piston head can move in or out. Because my system is at some pressure, that pressure is going to generate a force that pushes against the piston head. And so if in pushing against that piston head, it moves the piston head from where it's initially drawn here in the picture further out, say to where this dotted line is, then I know that the force and the displacement point in the same direction, which means that the work done by the system has to be positive. So the force exerted by the system on the piston head, the displacement, both of those pointed in the same direction, so the work done by the system is positive. So this means that when the volume increases, or another way of saying this is when our system expands, then the work done by the system is positive. Well, this equation tells us that if the work done by the system is positive, then the work done on the system is negative. On the other hand, the pressure from my system is pushing against the piston head, but what if the piston head moves to the left? So it moves against that force. Well, in that case, that would mean that the work done by the system would be negative. And so when the volume decreases, or when my system compresses, the system does negative work. Well, how is it that the system's going to compress? If the piston head moves from, say, where this dotted line is to where it's pictured initially, so it is moved to the left in this picture, the only reason it would have done that would have been because there was an even larger force out here pushing on the piston head that did work on the system by compressing the piston head in. So you can see that when your system is compressed, why it's compressed is because there had to be work done on the system. And of course this equation tells you that if positive work was done on the system, then that meant that the work done by the system had to be negative. So from our mechanical interpretation of work, we said that the work done by something is equal to the area under the curve in a force versus position plot. So if we think about this as just a one-dimensional work term, so that we've got the x component of the force on the vertical axis, the position in x on the horizontal axis, then as you go from some initial position to some final position, the work done by the force over that displacement is going to be given by the area under the curve. Well, of course, we can calculate out what that is, right? And so if it's a constant force, then it's just the x component times delta x. And what I'm going to do is I'm going to take that equation and multiply it by a unique version of the number 1. So in this case, the number 1 is going to be equal to the area the force is exerted over divided by the area. So obviously something divided by itself is 1. I can multiply anything by 1 and haven't changed the equation. And so all I'm going to do now is I'm just going to break up these two area terms so that the one on bottom goes with the force and the one on top goes with my delta x. And so what I see when I do that is that the force per area, that's our definition for pressure. Area times some little length, well, area times length is a volume. So A times delta x, the area times delta x, is equal to the change in the volume of the system. So I can reframe this equation as the work done by the system is equal to pressure times some volume change. And so what this means then is that I can think about the area under the curve on a pressure versus volume plot. So if I put pressure on the vertical axis, volume on the horizontal axis, then when I go from some initial state to some final state, the work done by my system is simply going to be the area under the curve that shows how I progressed from my initial to my final state. So part of why we're going to care so much about PV diagrams in thermodynamics problems is because PV diagrams will let us see the work done by the system by looking at the area under the curve when you plot out the process that you go through in going from some initial state to some final state. Now the other thing to keep in mind, of course, is that when our system expands, we know that it does positive work. So thinking about the sign of the work done by the system, looking at our PV diagram, really is as simple as, well, did you go to the left or to the right? So if you went to the right, your system expanded, the work done by the system had to be positive. On the other hand, if you move back to the left, that means your system was compressed, the work done on the system would have been positive, and the work done by the system now has to be negative. So that's talking about the two individual terms. So coming back to think about the first law and what it's telling us in general is, again, it says that we can keep track of how the thermal energy of our system is changing by thinking about how these two energy exchanges happen over any particular single process, which means that you can increase the internal energy of your system by either transferring energy into the system as heat or by doing work on the system. So if positive work is done on the system, then that work done by a term is negative. That negative work is going to cancel with that negative sign, and again you increase the internal energy. On the other hand, the internal energy of the system tends to decrease if energy is transferred out of the system as heat, so it's lost rather than absorbed, which means that Q is negative, or work is done by the system. So this work by term is positive, but it's being subtracted. So what we want to think about when we're using the first law of thermodynamics is how these two energy exchanges are occurring, and in some sense, which one is winning. If more energy is transferred in as heat than work is done by the system, then you're increasing the energy of your system. On the other hand, if your system does more work, so if more work is done by the system, then energy is transferred into the system as heat, then delta E will be negative. So we'll talk about thermodynamic processes where we'll need to be careful about keeping track of the balance between these two terms. So just as a final example, we'll look at a process where all the energy transferred into a system as heat will be converted into doing work by the system. So in that case, these two terms will both be positive, they'll both be the same, and so when we subtract them, it'll tell us that the internal energy of your system isn't changing during that process. So what we want to do is get comfortable with using the first law to keep track of the total energy of our system.